some talks which reflect the title of the workshop, so maybe a little bit about oscillations, later turbulence. The first speaker is Barbara Ferreira, and she's going to tell us about warp and eccentricity.
Hi, I'm Barbara, and I'm working with Gordon Ogilvie in Cambridge. I'm a PhD student, and I'll be talking about warp and eccentricity propagation in disks around black holes. And to start with, why should we talk about warped and eccentric disks? Well, because there is increasing evidence, both observational and theoretical, that disks around black holes may be warped and eccentric, from the Bardeen-Peterson effect to fairly recent detections of misalignments of jets. So the jet of that black hole candidate, which is thought to be aligned with the rotation axis of the black hole, is measured to not be perpendicular to the binary orbit. So there is a misalignment, and that's evidence for a warp. And warps have been studied by Ivanov and Illarionov and Lubo et al., and they found that in the low viscosity limit, the warp has an oscillatory radial structure. There is also evidence for eccentric disks. Eccentric disks have been widely studied in the context of cataclysmic variables, where they are thought to exist, where the mass accretion ratio is less than 0.3, and they have been used, and precessing eccentric disks have been used to explain superhump phenomena. And recently, there are a lot of papers of observers that think they detect superhumps in black hole binaries, so it's evidence for eccentric disks in black hole binaries. And Lubo in '91 studied tidal instability, and he found out that an eccentric mode can be excited in the 3-to-1 resonance in the disk, and which is in the outer part of the disk. And so it is excited in that region, and it propagates inwards. And there is a similar idea for warped disks, so that's why in the Lubo et al. Paper, Lubo et al. 2002 paper about warped disks, there's this idea that the warp is excited in the outer part of the disk and it propagates inwards. So it's this inward propagation that I'll be talking about. And the idea is that these global deformations propagate inwards and they reflect at the inner boundary if a no torque boundary condition is imposed and a stationary wave is set up. But actually why me and Gordon decided to study this inward propagation of warp and eccentricity has to do with our previous work on wave excitation and high-frequency QPOs. So if we believe Kato's idea that high-frequency QPOs are inertial waves trapped in the inner parts of the disk, then there's this possibility of a coupling mechanism which involves global deformations through which these inertial waves can be excited. And the idea of the mechanism is that the R mode is what everyone calls G mode. It's the inertial mode. So an axisymmetric R mode couples with a warp which can be identified with an m equals 1, n equals 1 mode, where m is the azimuthal wave number and n is the vertical wave number, or with the eccentricity, which in this treatment, again, it's identified with an m equals 1 mode, n equals 0 mode. And the idea is that this inertial waves couple with global deformations, and in this coupling an intermediate mode arises, and this intermediate mode propagates to the left of its co-rotation resonance, so it has negative energy, and when it's damped into the disk, either by approaching its co-rotation resonance or the marginally stable orbit, it damps its negative energy into the disk, so it removes positive energy which becomes available for the R mode to grow, and this is the basic idea of the mechanism. Of course, for all this coupling to work, the global deformations need to reach the inner region of the disk where the inertial modes propagate. And they need to reach it with a reasonable amplitude so that the growth rate is big enough, and maybe big enough, to avoid the modes being destroyed by MRI turbulence. And in the first work, we studied the warp and eccentricity we did a local analysis of these modes because of all the coupling involved. There were complicated nonlinear terms. But now, because we are studying them isolated, we can use the more appropriate secular theories of Lubo et al. And Goodchild and Ogilvie for the case of the eccentricity. So in these equations, W is the warp tilt at each radius, P is the vertical integrated pressure, sigma is the surface density, and alpha W is parametrizing the damping of the warp. So it's not necessarily equal to the Shakura-Tsunayev alpha in the sense that it's related to another stress, to another component of the stress tensor. But it's just a simple way that we have of making the warp be damped so that we can study the viscosity effects. And similar for the case of the eccentricity, we have alpha E. Alpha E in this case is actually about viscosity because this is a very simple 2D theory and there are complications about including a real viscosity in eccentricity theories. But Gordon did a lot of work on that in 2001, etc. And the frequencies, for the characteristic frequencies, we'll use the relativistic expressions. So the orbital frequency omega is described by that. Then the epicyclic frequency and the vertical frequency. And A is the spin of the black hole. And to study, so the other things we need to plug in into the equations are sigma and P. So we need to study these equations in the context of a disk model. And we introduced this disk model, which has a polytropic vertical structure, combination of gas and radiation pressure, constant opacity. So it's basically similar to regions A and B of the Shakura-Tsunayev model, but with the addition of the polytropic vertical structure. And regions A and B are the inner regions, so are the regions we are most interested in. And with these assumptions and the disk equations, we get to these expressions for sigma P. H is the density weighted semi-thickness of the disk, and beta here is the ratio between radiation and gas pressure. So once we solve this equation for beta, we get expressions for H and sigma. And as I said, the model is similar to regions A and B of Shakura-Tsunayev. In region A, when we get the expressions for region A in the limit beta much bigger than 1, and for region B and beta much less than 1. So now we have everything. We can plug in both the frequencies and the expressions for sigma and P onto the equations for the warp and eccentricity, and we can solve them. Oh, and I forgot to say, sorry. So m dot is the mass accretion rate in units of Eddington, alpha is the Shakura-Tsunayev viscosity parameter, m is the mass in units of the solar mass.
You're assuming a total pressure stress when you...
Yes. And we solve these equations first in the undamped case, so we are assuming that alpha W and alpha E are 0 in this case. And we use a black hole of 10 solar masses and of moderate spin, so A equals 0.5. Gamma, which is a ratio of specific E's, varies with beta, but it is between those values. And because we are trying, in a way, to reproduce the state transitions that black holes go into, so from the low state to the high state and the very high state, we vary the mass accretion rate. I know it's not a one-to-one relation between a mass accretion rate and state transitions, but it's a simple model, and it's the best we can do to kind of try to mimic that. And we start by solving the equation for the warp, and we see that, so we have a constant tilt at outer radius, as expected, and we have this oscillatory radial structure as predicted by Lubo et al. And Ivanov and Ilarianov. And the wavelength increases with radius until it gets, well, sort of constant. And then as we increase the mass accretion rates, the wavelength in the inner region increases. And if we go to really high mass accretion rates, we practically lose all the wavelengths, so we just have a hump there.
You remind us what W is?
Oh, W is the warp tilt at each radius. Oh, and E, I'm now showing the results. Oh, and this is normalized to the outer radius. And so for the eccentricity, we have similar results. E is the eccentricity at each radius, and we also have the oscillatory radial structure. It doesn't tend to a constant at large radius, and I'll explain why in a second. And as we increase the mass accretion rate, the wavelength increases, as in the case of the warp. And all these results can be explained in light of the WKB theory. So if you go back to the equations of Lubo et al. And Goodchild and Ogilvy, we can make a WKB analysis of those equations, and we get these results for W and for E. And we can see from this results that the wavelength scales with the semi-thickness of the disk and the radius in that way, which implies that in the limit where beta is much larger than 1, so this is the region A, the pressure-dominated region, it scales with m dot, and when beta is much larger than 1, it scales with m dot to the 1/5. But in any case, the point is that it is expected that the wavelength increases with m dot. Similarly, for the eccentricity, we also have the increase with m dot in both regions. The amplitudes of our solutions also agree perfectly with the WKB predictions, at least in the region where the WKB's theory is more exact, which is in the inner region. And in this case, so as we see there, the dashed dot lines are the WKB predictions, and the others, the full line, is the numerical solution. And for the case of the eccentricity, we see that when beta is much less than 1, so we are in the gas-dominated region, the amplitude increases slightly with R, and that's why the eccentricity doesn't go to a constant value. And now that we have seen the undamped...
what is E out, though, since we can't tell from the plot there? What is
E out is the eccentricity at the outer radius.
What value is it? Does it have a number?
Well, it doesn't matter.
It doesn't matter. Yeah. Right. Okay. Never mind.
Well, it makes more. This normalization makes more sense in the case of the warp because
right.
we actually get.
Yeah.
But we just use the same. And the WKB analysis can also be used in the case of damped propagation. So now we use alpha W and alpha E different from 0. And we see, and the WKB analysis predicts that the amplitude of these modes will be attenuated. And so basically, W and E will have that term multiplied. In the WKB solutions will have that extra term. And that extra term tells us that the viscous attenuation is more important when alpha E, and where alpha E can be either alpha W and alpha I can be either alpha W or alpha E. So when the viscosity is high and the semi-thickness of the disk is low, this is a case where the viscous attenuation is stronger. So basically what this tells us is that if we fix the viscosity, then as we increase the semi-thickness of the disk, the viscous attenuation will be less important. And indeed we can see that, this in our results. And so that we can see this better, I'm actually going to use quite reasonably high values of alpha W and alpha E. So for the case of the warp, I use alpha W equals 0.15 because in this case, when I use m dot equals 0.2, the warp does not reach the inner region, or it only reaches the inner region with 0 amplitude.
Can I just ask a clarify? When you did, I realize that m dot is the accretion rate divided by the Eddington accretion rate, but
yeah.
do you include the efficiency factor in that definition or not?
Yes, we use an efficiency factor of 0.1.
Okay, so it's L over eta c squared
yeah.
divided by L at eta. Okay.
Yeah. So when I increase the mass accretion rate, we see that indeed the amplitude in the inner region starts increasing. I still have the effect of the increasing in the wavelength, as we have seen in the undamped propagation case. And again, when I increase m dot, again I have more amplitude, more warp amplitude in the inner region. And we have similar results for the eccentricity. For the eccentricity, I actually have to use an even higher value of alpha E to get 0 amplitude when m dot is 0.2. But I still get, when I increase m dot, I still have the increase of the amplitude in the inner region. Yeah. So, and before I go on to the possible observational implications of these results, I'll just summarize my talk. So we have seen that global deformations may be common in black hole binaries, and they can propagate as stationary waves of reasonably long wavelength, and reasonably long is in the sense that it's much larger than the disk thickness. And they can propagate to the inner region under a wide variety of conditions. So the coupling mechanism we talked before may be initiated under a wide variety of conditions. And in real disks, where there's actually viscous damping. If this viscous damping is high enough, the warp and the eccentricity may only reach the inner region with reasonable high amplitude when the mass accretion rate is big enough. And if we believe that certain observational papers that say that in the very high state where high frequency QPOs are mainly detected, the mass accretion rate is maximum, then, and if we believe Kato's model that high frequency QPOs can be identified with this inertial waves trapped in the inner regions of the disk, then this might explain why we only detect high frequency QPOs in the very high state.
You've made up significant time. You were rushing through your results, so I think we have more time for questions and discussion. So, other questions?
So this stationarity is critically dependent on this no torque in a boundary condition, is that right? The stationarity of the wave is critically dependent on the standing, the fact that you get a standing wave.
Yeah, it reflects because of that boundary condition.
But of that no torque boundary condition.
But
so
it's not, but I'm not imposing that boundary condition necessarily at the marginally stable orbit. I mean, indeed, the equation, I'm actually solving the equation slightly to the right of the marginally stable orbit, just because the model, the disk model, has a singularity there.
Right. The stationary disk model has a singularity.
Yeah, exactly.
So if you had some non-zero inner torque, and you may know that people have argued about this.
Yeah.
What do you think would happen? I mean, this is related to whether the thing would precess. I don't know.
I'm not sure.
Okay.
I haven't tried.
Okay.
In this respect, there's a very small detail, and maybe I misunderstood the physical meaning of the quantity which you call F. I think your F is 1 minus square root of R in over R. Then you are using Kerr geometry expression
Yes,
for
the
omega,
model-
and it
the
is
model-
not consistent.
The model is
Yes.
Newtonian, and the
Yes,
justification for
exactly.
using a Newtonian model comes from the equations. So,
But when we are talking about where the torque is zero and this kind of things, then it is slightly relevant.
yes, it is, but our argument is that no, sorry. The argument is that the terms that dominate in these equations that describe the warp and eccentricity propagation are the frequency terms. Okay. So this one and this one.
Yes, yeah, I agree with you, and I have no problems with this F. I only noticed that you use
Yeah,
for
yeah.
omega
It is. I
Kerr
do
and
agree
for
that it's
F
not.
Newtonian.
I do
Yes.
agree that it's not perfectly consistent. We just argue that the most important terms are those ones, so that's where the relativistic effects are most important.
Yeah, I had a question about the possible effect of the vertical structure. So one of the things with spiral density waves, which essentially is sound waves that people have discussed, is that the temperature at the midpoint is higher than away from the midpoint. And that means sound waves propagate faster, and so effectively when you propagate one of these spiral density waves, you can actually diffract or refract it, and effectively dissipate it away towards the, effectively you disperse the energy in the wave. So I'm wondering whether there could be, because you need this standing wave, you need actually many, to create a standing wave, you need many back and forth.
Oh, so you mean, yeah.
Would there be such an effect that could be a problem with, now you have inertial waves, so they don't necessarily have this problem, but I'm just wondering whether you have thought about it.
I don't know. I haven't studied.